When determining the required amperage rating for individual unit panels and their corresponding feeders in a multi-unit dwelling, the total calculated load for each unit is the determining factor. The demand factor of 41, derived from NEC Table 220.32, applies exclusively to the service size calculation. This calculation determines the appropriate size of the main service entrance conductors, as well as the main circuit breaker or fuses protecting the entire service. This demand factor does not extend to the individual unit panels or the feeders supplying power to those panels. It is essential to understand that each individual unit panel must be rated to handle the full potential load of the unit. While the overall built-in load benefits from a demand factor due to the statistical unlikelihood of all units simultaneously drawing their maximum power, each unit must be independently capable of supporting its maximum load at any given time. The electrical wiring, overcurrent protection devices such as circuit breakers or fuses, and the panel itself must be sized appropriately to accommodate this maximum potential load. Consider a scenario where each unit is equipped with various appliances and electrical devices. If each unit panel and feeder was sized based on the reduced load obtained after applying the demand factor, there would be a risk of overloading the system if multiple units, or even a single unit, were to operate at or near their maximum capacity. This could result in nuisance tripping of circuit breakers, potentially damaging equipment, and even creating a fire hazard. To ensure electrical safety and reliability, the NEC mandates that the individual unit panels and feeders be sized to handle the total calculated load for each unit. This load is determined by adding up the amperage requirements of all connected devices and appliances within the unit, taking into account any applicable diversity factors for specific types of loads. Diversity factors recognize that not all connected devices will operate simultaneously at their maximum rated power. For example, lighting circuits may have a diversity factor applied, as it is unlikely that all lights within a unit will be on at the same time. However, it is crucial to apply diversity factors judiciously and only when there is a reasonable basis for doing so. In the absence of specific information supporting the application of a diversity factor, it is best to err on the side of caution and assume that all connected loads may operate simultaneously. Once the total calculated load for each unit has been determined, the appropriate size of the unit panel and feeder can be selected. The panel must have a sufficient number of circuit breaker spaces to accommodate all of the branch circuits required to serve the unit's various electrical loads. The feeder conductors must be sized to carry the total calculated load continuously without exceeding their ampacity rating. The ampacity rating of a conductor is the maximum amount of current that it can safely carry without overheating. The NEC provides tables, such as Table 310.15b16, that specify the ampacity ratings of various types of conductors based on their size, insulation type, and installation conditions. In addition to the feeder conductors, the overcurrent protection device, such as a circuit breaker or fuse, must also be sized appropriately to protect the conductors from overload. The overcurrent protection device should have an ampacity rating that is no larger than the ampacity rating of the feeder conductors. This ensures that the conductors are adequately protected from excessive current flow. It is also important to consider voltage drop when sizing the feeder conductors. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of lighting, and even damage electrical components. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits. To minimize voltage drop, it may be necessary to increase the size of the feeder conductors. This will reduce the resistance of the conductors and decrease the amount of voltage drop. In summary, the individual unit panels and feeders in a multi-unit dwelling must be rated for the total calculated load of each unit. The demand factor used for the service size calculation does not apply to the individual unit panels and feeders. By sizing the unit panels and feeders appropriately, you can ensure electrical safety, reliability, and compliance with the NEC. The process involves firstly calculating the total connected load for each unit, accounting for any applicable diversity factors. Secondly, selecting a panel with sufficient breaker spaces to accommodate all branch circuits. Thirdly, sizing the feeder conductors based on the total calculated load and voltage drop considerations. And fourthly, choosing an overcurrent protection device with an ampacity rating no greater than the feeder conductor ampacity. This approach ensures that each unit can safely and reliably operate all of its electrical equipment without overloading the system. Consider a practical example. Suppose a 12-unit apartment building has each unit with a total connected load of 36,360 volt amps, which translates to 151.5 amps at 240 volts. The demand factor from table 220.32 for a 12-unit apartment building is 41. If we were only concerned with the service entrance conductors, we would apply this demand factor to the total connected load of all 12 units. The total connected load of all 12 units is 12 times 36,360 volt amps, which is 436,320 volt amps. Applying the 41 demand factor, we get a service demand load of 436,320 volt amps times 0.41, which equals 178,891.2 volt amps. This is used to size the service entrance conductors and main overcurrent protection. However, when sizing the individual unit panels and feeders, the demand factor is not applied. Each unit panel and its associated feeder must be sized to handle the full 36,360 volt amps, or 151.5 amps. This means that each unit panel should have a main breaker rated for at least 152 amps. The feeder conductors supplying each unit panel must have an ampacity of at least 152 amps, after applying any applicable correction factors for ambient temperature or the number of conductors in a raceway. Let's delve deeper into the specifics of calculating the total connected load for each unit. This calculation involves itemizing all of the electrical loads within a unit and determining their individual amperage requirements. Common electrical loads in an apartment unit include lighting, receptacles, appliances, and heating and cooling equipment. For lighting, the load is typically calculated based on the wattage of the lighting fixtures. The wattage is then divided by the voltage to determine the amperage. For example, a 100-watt light bulb operating at 120 volts draws approximately 0.83 amps. For receptacles, the NEC requires a minimum load allowance of 180 volt amps per receptacle outlet. This is to account for the potential for multiple devices to be plugged into a single receptacle. The amperage for receptacles is calculated by dividing the volt amp allowance by the voltage. For appliances, the load is typically specified on the appliance's nameplate. The nameplate will indicate the appliance's voltage, amperage, and wattage. The amperage rating should be used for load calculations. For heating and cooling equipment, the load is typically specified in volt amps or kilowatts. The amperage is calculated by dividing the volt amps or kilowatts by the voltage and power factor. The power factor is a measure of how efficiently the electrical power is being used. Once the amperage requirements for all of the electrical loads within the unit have been determined, they are added together to arrive at the total connected load. As mentioned earlier, diversity factors may be applied to certain types of loads. For example, a diversity factor of 0.75 may be applied to lighting circuits, recognizing that not all lights will be on at the same time. Similarly, a diversity factor may be applied to receptacle circuits, recognizing that not all receptacles will be in use simultaneously. However, it is important to exercise caution when applying diversity factors and to only do so when there is a reasonable basis for it. After calculating the total connected load, the next step is to select the appropriate size of the unit panel. The panel must have a sufficient number of circuit breaker spaces to accommodate all of the branch circuits required to serve the unit's various electrical loads. Branch circuits are the circuits that extend from the panel to the individual electrical loads. For example, a branch circuit may serve a lighting circuit, a receptacle circuit, or an appliance. The NEC specifies the minimum number of branch circuits required for various types of occupancies. For example, the NEC requires at least 2 small appliance branch circuits for dwelling units. These circuits are used to serve small appliances such as toasters, coffee makers, and blenders. In addition to the minimum number of branch circuits, it is also important to consider the future electrical needs of the unit. It is generally a good idea to install more circuit breaker spaces than are currently required to allow for future expansion. Once the number of circuit breaker spaces has been determined, the panel can be selected. The panel should have a main breaker with an ampacity rating that is equal to or greater than the total calculated load. The panel should also be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories. After selecting the panel, the next step is to size the feeder conductors. The feeder conductors are the conductors that run from the service entrance to the unit panel. The feeder conductors must be sized to carry the total calculated load continuously without exceeding their ampacity rating. The ampacity rating of a conductor is the maximum amount of current that it can safely carry without overheating. The NEC provides tables that specify the ampacity ratings of various types of conductors based on their size, insulation type, and insulation conditions. When sizing the feeder conductors, it is important to consider voltage drop. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of lighting, and even damage electrical components. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits. To minimize voltage drop, it may be necessary to increase the size of the feeder conductors. This will reduce the resistance of the conductors and decrease the amount of voltage drop. In addition to the feeder conductors, the overcurrent protection device, such as a circuit breaker or fuse, must also be sized appropriately to protect the conductors from overload. The overcurrent protection device should have an ampacity rating that is no larger than the ampacity rating of the feeder conductors. This ensures that the conductors are adequately protected from excessive current flow. Finally, it is important to ensure that all electrical work is performed by a qualified and licensed electrician. Electrical work can be dangerous, and it is important to follow all applicable codes and regulations. A qualified electrician will have the knowledge and experience to perform the work safely and correctly. In summary, sizing apartment unit panels and feeders requires careful consideration of several factors, including the total calculated load, the number of branch circuits, voltage drop, and overcurrent protection. By following the guidelines outlined in the NEC and working with a qualified electrician, you can ensure that the electrical system is safe, reliable, and code compliant. Remember, safety is paramount when working with electricity. Always to energize circuits before working on them, and never take shortcuts. Electrical codes are in place for a reason, and it is important to follow them carefully. By taking the time to do the job right, you can protect yourself, your family, and your property from electrical hazards. When dealing with electrical calculations and installations, always consult the latest edition of the National Electrical Code and seek guidance from qualified electrical professionals to ensure compliance and safety.